Hey guys, welcome to our lecture for estimating population proportion and also estimating population means. The really cool thing with this lecture is we're going to talk about kind of how we estimate these things using samples, and also one thing that I'm sure we've all been thinking about throughout this term, how big of a sample size do we need to have for certain things? So let's get started. Part one of this section, we're going to talk about the proportions. Part two, we'll be talking about means. So it's kind of broken up again into two parts. So this part, we're going to talk about proportions. We're first going to talk about point estimates, kind of what they are, what's the best point estimate for a population proportion. We'll move into confidence intervals, which are what we're going to use to estimate the population proportion and some of the population means. And then we'll talk about sample size. So a point estimate is really simple. Okay, it's a single value that is used to estimate some parameter of a population. Okay, for a sample proportion, that's our p hat. That's what this little symbol means. Okay, instead of x bar for sample mean, sample proportion is p hat. That's our best point estimate for the population proportion. In other words, basically, p hat is trying to gauge, mathematically speaking, is going towards what p actually is. So lowercase p is our representative of population proportion. So we talked about something that's an unbiased estimator. So an unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. What this just means here is if we collect all of the samples possible and we look at the collection or the distribution of the, in this case, sample proportions, or p hats, the mean of that distribution would be the mean of our population. Okay, so just what we talked about kind of with central limit theorem. So x bar is an unbiased estimator. You're not going to be tested on unbiased estimators or biased estimators. I'm not worried about that. I just want to let you guys know what those were. So we have this example. A Gallup poll was taken in which 1,487 adults were surveyed. 640 of them said they have a Facebook page. Based on this result, we can get the best point estimate for the proportion of all adults who have a Facebook page. Now, there's a couple issues with this survey, first of all. One is really just kind of the words. It says a survey was taken of 1,487 adults. Where were those adults? How was this taken? Right? We don't know anything about how the survey was done. Now, it's safe to assume this was a good survey with good questions and a random sample, especially because Gallup poll is a pretty reliable source. But for the purpose of this example, we're going to suspend any issues of, kind of, was this a good sample, unless I specifically ask you, assess if this was a good sample. Okay? So, really simply, all we have to do is find the proportion from this sample by taking the number that have Facebook accounts over the total number surveyed, so 640 over 1,487, and we get 0.43. So that tells me that our best point estimate is our p hat here, and that is 0.43. If we want to, we can turn that into an interpretation using percents, and we could say that approximately 43% of all adults have Facebook pages based on this survey. So that's how we can use point estimates. Let's talk about confidence intervals. Okay, this is creating a range or an interval of values that we can estimate the true value of a population parameter. Okay, now the chances of the population proportion being exactly 0.43 is pretty small, but what confidence do we have? How kind of close are we? Are we saying, oh, we're within 1 or 2%, or within like 10% either way, right? So that idea is really kind of a big deal, right? If we say, oh, we're really confident this is within 1%, so then that means, okay, so it's either 42 to 44. But if we're saying, we think it's within 10%, okay, so it's 33 or 53. That's a much different range, right? So our level of confidence is something we're going to talk about in a bit, and that's going to apply to our confidence intervals, which is what that is created by. So this confidence level, okay, we usually say like we're 95% or 0.95, things like that. And that comes from this really simple kind of equation of 1 minus alpha. This alpha is going to be an important thing that we utilize later. Now, you're not going to say I'm 1 minus 0.05% confident or something like that. You would say I'm 95% confident. Okay, so in those cases, you would just go for that. Other terms that we use sometimes are degree of confidence or the confidence coefficient. I'm pretty much going to always stick with confidence level. So this is some of our most common confidence levels that we use: 90%, 0.9, 95%, 0.95, 99% or 0.9. And those correspond to alpha values of 0.1, 0.05, and 0.01. Notice all we're doing to find this alpha value here, 0.1, is we're taking 1 minus 0.9 to give us our alpha value. Okay, so pretty easy, pretty straightforward. All right. Now, let's real quick take a break from kind of all this, and we're going to talk about how we interpret this. So let's say, for instance, that I have a confidence interval for my population proportion that is 0.405 is less than the population parameter, the population proportion, which is less than 0.455. A good way to interpret this at a 95% confidence level would be to say that we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. Okay. Now, it is not correct to say there's a 95% chance the true value will fall within there, or 95% of sample proportions will fall between there. Okay. So we are 95% confident that that interval does actually contain the true value. Okay. Now, where does this alpha come in? This alpha comes in finding our critical values. We've talked about critical values in the past. We've talked about them just simply as z sub alpha, right? And a z sub alpha is simply a z-score, so it's on the standard normal distribution, that has an area of alpha to its right. Now, there's a couple of different things here that we can do, and one of the things we do, because we're finding these intervals, instead of wanting just area to the right, we want a kind of an equal area. We want to get this middle range. And so instead of using z sub alpha, we use z sub alpha over 2, so that the combined area in the two tails gives us that alpha, that possible kind of error. So we say that a critical value is the number on the borderline separating sample statistics that are significantly high or low from those that are not significant. The number z sub alpha over 2 is a critical value that is a z-score with a border, with a property that it is on the border that separates an area of alpha over 2 in the right tail. So our z sub alpha over 2 is still going to be this critical value over here with an area of alpha over 2 to the right. Okay, so the same way we talked about this when we talked about continuous distributions and we talked about the normal distribution first last week, we talked about finding these critical values, and this is how we're going to do it. Same thing applies. The only difference is instead of z sub alpha, we have z sub alpha over 2. Now, I want to make a quick distinction. This is kind of hard verbally, but I'll try and make my pauses appropriate. This is not z sub alpha divided by 2, but it's z, and then in the subset is the alpha divided by 2. So we're not dividing z sub alpha by 2, but we're dividing alpha by 2. Okay? So how do we find these? So let's find the critical value, z sub alpha over 2, corresponding to a 95% confidence level. It's really simple. We're going to use our calculator to do this. It's really not hard. The first thing we have to do is figure out our alpha, okay? And our alpha is 0.05. So if alpha is 0.05, that means alpha over 2 is simply 0.05 divided by 2, or 0.025, okay? Now, all we need to do is use our calculator with inverse norm. Now remember, z-scores are on standard normal, so we know the mean is 0, standard deviation is 1. So using our calculator, we can do inverse norm, and let's actually pull that up. Pull that up. Nope, not gonna let me. Gotta exit out of this. There we go. All right. So if we use our inverse norm, okay. Now here's a cool thing. We can type everything in here. So I know my alpha over 2 is 0.025. Now remember, inverse norm does area to the left, but z sub alpha is area to the right. So I know there's 0.025 area to the right. So to get the area to the left, I simply need to do 1 minus 0.025. And now you can absolutely do that calculation before and then enter that number in here, the resulting number, 0.975. But you can also enter the calculation in here, and your calculator can handle that no problem. Now again, because it's a z value, our mean is 0, standard deviation is 1. So go to paste. Remember, if you have the calculator just gives you this setup here, you would still just type that in just like you would before, for the area, comma mean, comma standard deviation. And we get 1.95996. which comes to be a nice 1.96. Okay, let's come back here. Look at our nice z sub alpha over 2 is 1.96. Okay. Now, this talks about using tables. Remember, we're not using tables. We're using our calculator because that's a much easier situation. So what this means, okay, if we look at this kind of graph here of a normal distribution, is between negative 1.96 and 1.96, we have 95% of the data. And so if we're capturing 95% of the data there, when we create our confidence interval using this critical value, we will create a 95% confidence level of the population parameter we're looking for. Now, a quick side question for you. If our confidence level gets bigger, in other words, we get more confident, does our range get bigger or smaller? In other words, our range, when I say range, is this value here, does that get bigger or smaller? Looking at this picture, it's really easy, right? If our confidence level gets bigger, so would our interval. And the way I like to think about it is if you think about a dartboard, okay? If you have a very small dartboard, I'm not very confident that I'm going to be able to hit that with the dart. But if I have a very large dartboard, I'm pretty confident I can hit that. So the bigger the target, essentially, and the bigger the interval, the more confident we are going to be. So as our confidence level increases, so does our interval size. Okay. Now, these are the three confidence levels that we talked about before, the most common ones, 90%, 95, and 99, their corresponding alpha values, and their corresponding critical values. If you go ahead and find these through these standard methods, which I recommend trying to do that once at least, make sure that it all makes sense, okay? You will see these are pretty easy to find, doing the exact same thing we did to get that 1.96. All right. Now, what we need to be able to calculate, we use these critical values to calculate the margin of error. If you think back to when we first had that 0.43, I said, I don't know, are we off by 10% or 1%? That would be our margin of error. And that is what we use to kind of create this interval, okay? So the margin of error is based off of our critical value, and we're just in our sample proportion. And very simply, the equation for the margin of error for a proportion is very simple. Our margin of error is the critical value times the estimated standard deviation of the sample proportion. And that's just very simply the square root of the sample proportion times 1 minus the sample proportion over n. So think back to binomial distributions. P was kind of success, Q was failure, right? And we know that to get Q, we just do 1 minus P. Same thing here. So in the example of Facebook, our P was 0.43. So in this case, our Q would be 0.57, or 1 minus 0.43. Okay. So here's some interval, some notation you need to make sure you understand. So just P is our population proportion, P hat is our sample proportion, N is the number of sample values, E is the margin of error, and Z sub alpha over 2 is our critical value. Okay. So here's the steps to construct a confidence interval for the population proportion. The first thing you have to do is verify the requirements are met. Now, the requirements are here. So not the preceding slides, but in the preceding slides. Once you know the requirements are met, you're going to use your calculator to get your critical value. Then you're going to figure out what your margin of error is. Once you've figured out your critical value and your margin of error, you're going to use that to construct your confidence interval by doing the sample proportion minus your error and sample proportion plus your error. And finally, you're going to round the result to usually 3 significant digits or whatever is specified for the individual problem. So, what are the requirements? First of all, simple. The sample is a simple random sample. Okay, we have to have a good quality random sample. We can't have a bad sample and then construct things off of that, because if it's a bad sample, it's not representative. The next thing, and this is the big one, the conditions for a binomial distribution have to be satisfied. Remember, there's 4 conditions for a binomial. It's that that there's a fixed number of trials. The trials are all independent. You have 2 categories. You either have a success or a failure, and the probability of a success remains constant for each trial. So we need to make sure we have those 4 things met. The next condition, the last condition, is that there has to be at least 5 successes and 5 failures. If there's not, it's not that our sample size is too big or too small. It's that our information gathered isn't good. We kind of run into some issues. Okay, so if you have something where a p is something like 99 or 0.99, right, where almost everything is that success or whatever you're looking for, it can be kind of challenging to do this just because it's hard to get those 5 successes and 5 failures without getting crazy large samples. So, very simply put, our confidence interval is going to be our point estimate. That's that p hat, our sample proportion, plus or minus the mean. And that's it. We're typically going to enter this, especially online, in interval notation. Okay, so that would be parenthesis, sample proportion minus the error, comma, sample proportion plus the error, close parenthesis. Okay, but also if you do plus or minus or use the inequalities, all 3 of these are perfectly acceptable answers unless obviously it specifies to use one or the other. So make sure you guys are aware of that. The rounding rule, typically 3 significant figures unless otherwise stated. So remember, significant figures are the numbers before zeros. So if something has a value of 0.0004598, those 000 do not count as our 3 significant digits. Our significant digits are the first numbers other than 0. Now, if it's 0.00030000597, it's going to be 0.0003. Okay? So once we get that first non-zero digit, that's where we start counting our significant digits. All right. So back to our Facebook poll. Okay. So we had 1,487 adults were sampled. 640 of them had Facebook pages. So we get that our sample size is 1,487, and our sample proportion, our p hat, is 0.43. So what we want to do is we want to find the margin of error that corresponds to a 95% confidence level, find the 95% confidence interval, and then based on that, can we safely say that fewer than 50% of adults have Facebook pages? So let's go through and do these together. So first thing we need to do is check our requirements. Okay, so the polling method used by the Gallup organization results in samples that can be considered to be simple random samples. This is basically saying check. And really, in this class, for the most part, it is going to be a check kind of system on that first one. I'm not going to give you things that are bad samples or are not a simple random sample. We're going to assume that they all are. Now, if you go on and work in some field where you're doing things like this in the real world, you need to make sure that your sample is actually a simple random sample. Okay. The conditions for the binomial experiment are satisfied because we have a fixed number of trials, the 1,487. Every trial is independent because one person's having Facebook doesn't mean the next person will have Facebook. You either have Facebook or you don't. And the probability remains fixed of having Facebook for any given point in time. Okay. Now the last condition is that we had 5 successes and 5 failures. So we have 640 people that have Facebook, clearly more than 5. And if we do 1,487 minus 640, we get 847, which is definitely more than 5 as well. So all 3 of our conditions check, and we are good to construct a confidence interval for this population proportion. So first thing we want to do is we want to calculate the margin of error. From the table, we know that our critical value is 1.96. From the sample, we know our sample proportion is 0.43. And to find our Q hat, we simply subtract 1 minus our sample proportion. 1 minus our sample proportion to get 0.57. And our sample size is 1,487. So we know all of the values we need to calculate the error. By simply substituting those values in and carefully evaluating this, you get an error of 0.025. So make sure you're careful when doing this on your calculator. One of the big things to make sure you're cautious of is that you're multiplying these before you divide, you're putting all of these in the square root. Sometimes what will happen is just this first piece will get put in the square root. These will be out. You need to make sure that when you're entering this in your calculator, you're being careful on how you do that. So now that we know what our margin of error is, we can construct our confidence interval simply by taking the sample proportion and subtracting the error. So 0.43 minus 0.025, and then taking our sample proportion and adding the error, 0.43 plus 0.025. Now, if it isn't already, as this one is, you would then need to round this down to 3 significant figures. So this is already down to 3 significant figures, so we're good. We can move on. So what this is saying is we're 95% confident that the true population proportion falls between 0.405 and 0.455. Okay. So based on that, does it appear that fewer than 50% of adults have Facebook pages? Well, yes, very simply. And the reason why is because 0.5 is entirely above the confidence interval. The highest our interval goes is 0.455, which is nowhere near 0.5. And so because of that, we can say yes to that last question. Okay. So here's a statement that summarizes the results. I'll let you guys read through that. I'm not going to waste our time. Let's keep chugging along. So we got to be cautious, and we never think that a poll results are unreliable if the sample size is a small percentage of the population size. The entire size of the population typically does not have any effect on how big of a sample you need to have a reliable sample. You might think, well, the sample size needs to be proportional to the population size. So if our if our population is 30, we could do a sample of 10. But if our population is 30 million, we would have to do a sample of 10 million. That's not correct. Okay, and that is why samples can work so well to help us make inferences about large groups of people or large amounts of things, by taking a sample of a small amount of them. Okay, so to determine the necessary sample size for a given population proportion, what we need to know is a few different things. These are some more notations, right? But what we have is 2 possibilities. If we have some estimate of what p hat is, okay, we can do this formula. And this is going to give us smaller numbers always than this formula. Okay, and what's happening here is, so by having some estimate, how can we have an estimate for the sample proportion if we're just now determining the sample size? Well, it usually comes from like previous studies or things like that. So like if we've, 5 years ago, they did a study and found that 20% of adults had Facebook pages. We could use that as an estimate for this to figure out what sample size we need. Okay. And if we don't have any estimate, so this is kind of worst case scenario, we have no idea about the proportion whatsoever, we just multiply by 0.25. Okay. Both times we have the critical value is squared and the margin of error is squared. Now remember, the margin of error is going to be a decimal, not a percent. So if I say what's the probability we're off by no more than 3%, we need to convert that 3% to a 0.03. Okay. So let's do it. If the computed sample size n, is not a whole number, so this is just rounding, always round up. And the reason why is because what these formulas give us is kind of the minimum sample size to satisfy what conditions we're giving them. If we go down, so if we have 1067.11 is what those give us, and we do 1067, we're not necessarily guaranteed to get those conditions. We need to go, this is the minimum value, and so we want to go to the next whole number up anytime we're dealing with sample size. Okay? So let's do this. So this gives a nice little story here about making online purchases, and kind of we want to construct an interval, a confidence interval. It's 95% confident to contain the true proportion of people that make online purchases. Now, we've got 2 cases. First case is assuming that a recent poll showed 80% of adults make online purchases. And the second situation is assume we have no other information. So this is basically saying Case A, we have an estimate for p hat. Case B, we don't. And that's it. So let's look at problem A. So since we want a 95% confidence level, we know that our critical value is 1.96. Okay, and let's come back here. And we say that 95% confident that the sample percentage is in error by no more than 3 percentage points. That was one thing I didn't read. We're in error by no more than 3 percentage points. So it means our margin of error, remember, we're not doing error as percent, so it's not 3%, but it's 0.03. Okay? So we know those values, they're critical values in our error. Now, because we have that estimate that a previous study said 80% purchase things online, we have an estimate for p hat being 0.8, and that means q hat is 0.2. Okay, so we substitute those in, carefully do those calculations, and that comes out to be 682.951. Because we have any decimal at all, we always round up, so we get 683. So that means to be 95% confident that we are within 3 percentage points of the population mean or population proportion on this situation, we would only have to sample 683 people. Pretty cool. Now, if we don't know anything, our critical value in our error stays the same, but instead of having the p hat and q hat, we multiply by 0.25. And that gives us 1,067.11. Again, we have any decimal at all, so we go up and we get 1,068. So if we have no estimate, we have to sample 1,068 people, or things, okay? Or people in this problem. So notice the difference. 683 when you had that estimate, 1,068 when we don't. Having a prior estimate is really helpful, but again, not necessary. 1,068 is not that many, considering this is a sample about the entirety of people, or we'll say American people. We'll stick with America. Okay. So that's it for confidence intervals for proportions. Okay, they're really simple. Follow the formula for error, and you're good to go. Okay. So part 2, we're going to be talking about the point estimate for population means, constructing a confidence interval for population mean, and determining a necessary sample size to estimate the population mean. Okay. Some notation you need to know for this. Mu is the population mean, n is the number of sample values, x bars are sample mean, and e is the margin of error. S, remember, S is the sample standard deviation. We have 2 different notations for or representatives of standard deviation. S is for sample standard deviation, and sigma is for population standard deviation. So make sure you guys are very clear on that. When you're reading through problems, it's very important that you understand whether you're given the sample standard deviation or if you're given the population standard deviation. Okay. So, point estimates, I don't know if I passed it or I deleted it. The best point estimate of population mean is the sample mean. Don't really need to go into any more detail than that. So here's our requirements for constructing a confidence interval for a population mean with sigma not known. So we do not know, we don't have any idea of what the population standard deviation might be. So to be able to do this, we need to know that the sample is a simple random sample, and either of these conditions are met. Either the population is normally distributed, or n is greater than 30. Now notice, those are the exact same conditions for the central limit theorem, okay? Namely number 2. So, really kind of similar ideas, things that we've kind of used in the past, we're now starting to bring up. So to find the first thing we need to do is find the critical value. And notice this is a t, not a z, but a t. The critical value t sub alpha over 2 is a critical t value separating an area of alpha over 2 in the right tail of the student t distribution. Degrees of freedom, df equals n minus 1. What in the world is t? What are degrees of freedom? What in the world is a student t distribution? We've never talked about this, and that's right, we haven't, but we're going to right now. Okay, so I just want to first point out critical value t sub alpha over 2. It's the exact same as z sub alpha over 2. We're looking at a value with an area of alpha over 2 in the right, but we're going to find it using a different distribution. And this is because we have no idea about the population standard deviation. That is why we have to use this different distribution. So let's talk about the student t-distribution. So if a population is normally distributed, then the distribution t equals x bar minus mu over s over square root of n is called the student t-distribution, and it's for all samples of size n. Okay. The student t-distribution is commonly referred to simply as the t-distribution. We just dropped the student. Now, a cool fun story. The origins of the t-distribution, or the student t-distribution, is actually from a person who worked at Guinness. Yes, not Guinness World Records, Guinness Beer. Guinness Beer Company has a very fine restrictive policy that any sort of intellectual property or anything like that that's created through the work that's done there is in-house property and cannot be published, cannot be shared. Because they weren't dealing with large samples and they didn't know the population standard deviation because every batch was different, one of their mathematicians there created this distribution, this way of kind of dealing with that situation. And to get around the kind of gag order that Guinness had on them, he published it under this anonymous pseudonym, Student. And because of that, it has become known as the student t-distribution. Pretty cool, fun story. Math and beer always relating is entertaining to me and just kind of a fun anecdote. So let's talk about how we deal with this. Degrees of freedom are critical to finding these things. We have to talk about the degrees of freedom because the t-distribution varies depending on the sample size. And so our degrees of freedom are based on the sample size. In particular, it's n minus 1. And so that is always used to kind of tell us what we're dealing with. Okay. So if we look at this graph here, we've got 3 different graphs going on. We have in green the standard normal distribution. That's this top one here. Okay. The red, the middle one, is a student t-distribution with a sample size of 12. And the blue is a student t-distribution with a sample size of 3. Now, if you just look at the peaks, you may be like, okay, so green goes higher, red goes lower, blue goes the lowest. But then when you look out here, okay, green is higher. And so what happens is the smaller the sample size you have, kind of the more spread out your values are. So if you were to think of these as standard, kind of equivalent of standard deviation, if the standard deviation is large, it's more spread out. If it's small, it's going to be more narrow and kind of have a higher peak. The smaller the sample size is, kind of the more spread out these get, okay? And the less kind of obvious and clear things become. So, it has the same general symmetric bell shape as the standard normal distribution, centered at zeros as well, okay? The standard deviation of the student distribution varies depending on the sample size, but it's always going to be greater than 1, where the standard normal distribution is exactly 1. And the sample size, as it gets larger, the student t-distribution gets closer to the standard normal distribution, which we kind of saw here. So, the margin of error is very simple. We'll come back to that. Let's talk about finding the critical values, T sub alpha. Okay. If we have a confidence level of 95% and we have a sample size of 15, how do we find these critical values? Okay. So because n is 15, our degrees of freedom is n minus 1 is 14. Okay. Because our confidence level is 95%, the area to the right of the T sub alpha over 2 is going to be 0.025, just like it was for the critical value when we did population proportions. Okay. We can use our calculators to do this. Okay. And there's 2 ways depending on which calculator you have. So let's first get out of here and let's grab a calculator out. Okay. So this is using an 84, a newer 84. If you have an older 84, it might be the other way, but I'm pretty sure it's only 83s are the other way. So if you have an 83, just hold tight, watch and absorb, and then we'll move on. We'll come to you. So you're going to go to distributions. And notice we have normal PDF, normal CDF, inverse norm. We have inverse T. So we want to choose option 4 if you have inverse T. Okay. 93s don't unless you've done some sort of an update onto your calculator, which I don't know if is even out there available. But we have inverse T. This works just like inverse norm, where it asks us the area to the left. Okay. But instead of asking us a mean and standard deviation, it asks for degrees of freedom. So to find the critical value corresponding to a 95% confidence level, it means the area to the left is 1 minus 0.025. Okay? And for this problem, our degrees of freedom, so our sample size was 15, degrees of freedom are 14. Paste that, we get 2.1447866681. Or as we saw in here, 2.145. Okay. Now, what if I have a TI-83? How do I do this? And for those of you with the TI-84 that have the inverse T, you can also do it this other way as well. You can pick whichever one you like better. But if you have the 83, this is how you have to do things. Okay. So write these down, write these steps down. Okay. If you ever forget them, come back and watch this video, or just Google how to find a critical T value in TI-83, and you're going to be able to find it. So, step 1, go to the stats menu. Step 2, go over to tests. We are going to stats to test. And you need to scroll down till you get to an option 8. Or I believe 8 most of the time, maybe different than 83. It says T interval. So stats, then test, then down to T interval. Okay. And you should see a screen like this. Even if you have an 83, the screen is all the same. We don't want to go based off of data. We want to go based off stats. So in that first option, you're going to press the left arrow that it's highlighting stats and hit enter. You should only have to do that one time. That shouldn't be something you have to do every time, but it's a good idea to make sure that it's on stats. And I mean, it'll be pretty obvious because it'll ask different questions. So once we've selected stats, we need to enter the mean, sample standard deviation, our sample size, and our confidence level. Now, to get the critical T value, and I'm going to tell you right now, I am going to ask you on the test, what is T sub alpha over 2 equal? So you can't just use a workaround and figure out the final confidence interval. I'm going to ask you those in between steps. So to get this sample standard deviation for this value, all we're going to use is we're going to use the square root of our sample size. Okay. So that is what we're going to use in there. And then our sample size is just our sample size. Now notice X bar I left 0, right? And that's because the T distribution has a mean of 0. Now our confidence level, we want the 95 confidence level, so you leave that as 0.95. Go down to calculate, and hit enter. And we get this. And what this is very simply is this right here, this number, is our T sub alpha over 2. So our T sub alpha over 2 is 2.1448 or 2.145 as we had in here. So I'll do that with you guys one more time, okay? So we go stat over to test, down to T interval. We need to make sure that our input is on stat, so INPT stands for input, so our input stats. Our mean is always 0. Our SX, our sample standard deviation, is always the square root of our sample size. N is just the sample size. C level is our confidence level. And we calculate. We want to pull the positive number in that interval. Okay? So, that is how we calculate a critical T value, or a T sub alpha over 2. Okay? So let's jump back over here. The margin of error, if we don't know, this is if we don't know the population standard deviation. Our margin of error is simply this critical T value times the sample standard deviation S, so S is our sample standard deviation, divided by the square root of N. Okay? This will give us our margin of error for the population mean if we do not know sigma. Okay. Now, what if we do know sigma? Well, that's easy. It's the same formula. except instead of a t-value, we're going to use the z-value. Because if we know sigma, we know what the standard deviation, and we can use the critical z-value, okay, not the critical t-value. So we use our z sub alpha over 2, the same ones from the table that we did before with population parameters. And then we take that known standard deviation of the population and divide it by the square root of the sample size. This right here, if you look, this is just simply the standard deviation of the sample means, right? That's our sigma sub x bar. Remember that from central limit theorem, okay? So what if we're given some data? Oh no. Well, we can handle this. We'll be all right. So we have these 15 birth weights of girls given below, for which the sample size is 15. The sample mean is 30.9 Hg. Hg is hectograms. That's listed kind of down below. And we want to construct a 95% confidence interval. Now, if you read the statement down below, it tells you what the standard deviation is of this sample, because I'm nice and I did that for you. Okay. So hectograms, this is just the last little sentence here. So the measurement weight here is in hectograms Hg. The conversion of hectograms to pounds is about 4.5 hectograms to 1 pound. Okay. So what would you do if I didn't give you anything except construct a 95% confidence interval for the population mean based on these 15 weights? I didn't tell you what the mean or standard deviation is. What would you do? Would you just panic? No, right? Because we know what to do here. Because we did this back in week, I believe, 3. We would very calmly grab a calculator and we would go into the list. We'd go to stat. We would edit our first list. We want to edit this so that it is these 15 numbers. So let's do that. So 33, 28, 33. 37, 31, 32. 37, 31. 37, 31, 32. 31, 28, 34. 1, 8, 34, 28, 33, 26, 28, 33, 26, and then lastly 30, 31, 28. 30, 31, 28. So if we highlight the very last entry, we can see that's the 15th entry. We have 15 values, so that's good. So once we have that, okay, quit, go back to stats, and remember, we want to calculate the 1-bar stats. And we get that we have a mean of 30.8666 repeating forever, or 30.9. And because this is a sample and not a population, the sample standard deviation is 2.9244, or 2.9, as given in the problem. Okay. If we wanted to go further, we could get our 5-number summary, right? All those breakdowns, you guys remember those. Okay. So that's how we would do this if we needed to use our calculator. Okay. First thing we have to do is check it. Is it a simple random sample? Right. Again, this is that kind of, yes, I'm not going to give it to you unless I say, like, is this a simple random sample? Then you might want to check. Since our sample size is only 15, that's not greater than 30. So we have to come back here. We go, okay, did this say anything about normal? Well, where's 15 girls to construct 95% confidence interval? Mean, we know that birth weights are normally distributed. Oh, we know that birth weights are normally distributed. That tells me that we are good to go. Okay. So Yeah, the standard deviation is the population, not the mean. It happens to be the sample mean, but it's also the population mean in this population standard deviation in this case. So condition 2 is check. So now we move on to finding the margin of error. Since we're looking at 95% confidence level, our critical value is 1.96. Easy enough. Standard deviation of the population is 2.9, and our sample size is 15. So we plug those into the equation for margin of error, and we get 1.96 divided by times 2.9 divided by square root of 15, which is 1.46760. So we can leave our error like that, nice and big and long, and then just round to one decimal place in the end, or we can round it now. It doesn't really matter too much. Okay. But either way, we take our sample mean and subtract the margin of error, and then we take our sample mean and we add the margin of error. We get this interval of 29.4 hectograms to 32.4 hectograms. So what this tells me is that with 95% confidence, we can say that the true proportion or true mean of weights of girls is between 29.4 hectograms and 32.4 hectograms. Okay. So here's kind of a quick little overview shot of what do we use. Do I need to find the T sub alpha over 2, or can I use the Z sub alpha over 2? Do I need to use that student T distribution, or am I good to use the standard normal? So what we are looking at is sigma is not known, and we're normally distributed population, or sigma is not known and n is greater than 30. If you have one of these two cases, okay, sigma is not known, population is normal, or sigma is not known and n is greater than 30, you are going to use the T distribution. The big key here is sigma is not known. However, if sigma is known and the population is normal, or sigma is known and n is greater than 30, you'll use the normal distribution. Now, in reality, in practice, in real world, it's not very often that we know what sigma is. But for this class, if I tell it to you, I tell it to you, and you have it. Okay. So make sure you're very cautious and aware of, am I looking at the standard deviation of the sample, or am I looking at the standard deviation of the population? Which one do I have? Okay. Now, if the population is not normal and n is less than or equal to 30, then we cannot construct a confidence interval for this situation. And that's it. There's some kind of tweaks and things that we can do and kind of like get this approximate interval, but for the purposes of this class, we can't do it. So let's find a sample size to find the population mean. So figure out how big of a sample do I need. Okay. We can only do this if we know the population standard deviation. Okay. There's methods to do this if we don't know it, and that's something that, if you were to take a further class in statistics, you guys would go over those more and more and kind of deal with this more in kind of a practical aspect of actually conducting samples. However, for the purpose of this class, if we don't know the population standard deviation, we're sunk and we can't figure out a necessary sample size. But the equation is very similar to the other one. One of the big differences is that the entire thing is squared and not the critical value and error separately. Okay. So again, we're going to go round up to the next whole number. We don't want to have, 63 and a half people sampled. We have to go to 64. Okay. And so we look here and we have that, assuming we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean, if it's believed that the population standard deviation is 15. Now, I want to say something here. So when we dealt with the proportions, that problem, we would find the sample size, we had an error of 3 percentage points. And because we had 3 percentage points, we needed to shift that from 3 to 0.03. However, here we're not dealing with percentage points. Our error is 3. Now, the entire thing is IQ points, and so that's why we have 3 IQ points. So it's kind of confusing with the points and points. But the difference is here, our error is 3, not 3%. And since it's 3, we leave it as 3 in our equation. We do not change that to 0.03. So again, this is one of the most common mistakes I see in these problems, is people converting mean errors of means to 0.03 and not when it should just be 3. So make sure you're kind of understanding, is the margin of error in a percent as it is with proportions, or is it a value like it is with means? So to do this, we simply plug our critical value corresponding to 95% confidence level. We have our known standard deviation of 15, and we have our margin of error 3. We plug those in, 96.04. So even though it's only 0.04, it still rounds up to 97. So that's crazy. This was talking about all statistics students. Not all statistics students in this class. All statistics students in America. We only need to sample 97 of them to be able to be within 3 of their IQ points. Pretty crazy. So, interpretation of that, pretty simple. It's pretty straightforward. Okay, with a random sample of only 97 statistics students, we will be 95% confident that the sample mean X bar is within 3 points of the true population mean. And that's it, guys. That is it for estimates. Go forth and conquer this assignment. I've extended the due date on it, so check that out. If this isn't spring term 2020, I have not extended due dates. They were what they were. Still check it, make sure. With that said, guys, enjoy the nice weather, or the rainy weather if it's winter term, and have a great one.